All right, good morning. What we're going to do is go over the test real quick. And yeah, we're going to do that first. Let's just say that. Okay, so test 3 here. Number 1 was this guy, x squared plus 4y squared minus 1. So the point is that the domain was all of the xy points where x squared plus 4y squared had to be bigger than or equal to 1. I mean, it's a square root, so the thing underneath has to be positive. For the range, you know for sure that these have to be z values that are bigger than 0. But can I get anything I want? And the answer is, well, look, I mean, x squared and 4y squared can get really, really big. And therefore, the range is just any positive numbers. It's closed. The domain is closed because it does include the boundary. And if you look at the level curves where you set this to be x squared plus 4y squared minus 1, probably should square both sides. You get c squared equals the square root of x squared plus 4y squared. Not square root, that's why you squared it. Okay, x squared plus 4y squared minus 1. And now you got to look at that and manipulate it a little bit, maybe, or just look at it and go, look, you got x squared and y squared, so it's either a circle or an ellipse. And you don't have a number in front of x, but you do in front of y. So these are just elliptical cross or level curves. So that was number 1. Number 2, probably can fit it in here. You just needed to do 2 different approach paths for the limit for x squared minus y squared over x squared plus y squared as you go to 0, 0. So if you approach from the top, that means x is 0, and you'll get negative y squared over y squared, and that's going to be 1, or minus 1. If you approach from the side, y is 0, and therefore you're going to get like x squared over x squared, and that limit's going to be 1. And so these are not equal, and therefore there's no limit on that one. 3, we did in class. The function is x squared y minus xy squared. You want to know what the answer is for f of 2.0 for f of 3.06, but we don't want to think too hard about this. So we like, well, I know what it is at 2, 3. If I plug in 2 and 3, I get minus 6. So it's got to be close to that. So how far off is it? And the answer is you create this df term, which is something dx plus something dy, and those somethings are the partial derivatives in here. So that's 2xy minus y squared, and the other one is x squared minus 2xy. And then you just evaluate this at x equals 2, y equals 3, and then the dx is 0.04, and the dy is 0.06. And if you plug all that stuff in, you'll get 3 times 0.04 minus 8 times 0.06, which ends up being minus 0.36. So then you just tack that on to your function, and you'll get that f of 2.04 of 3.06 is approximately negative 6.36 without having to do any fancy calculations or your calculator. 4, the math got a little tricky, but still it's just sines and cosines. So there's your r. You're going to need r prime, that's b. We probably need r double prime. So we get minus 5 sine, 3 cosine, and then we'll get minus 5 cosine and minus 3 sine. We do need the length of r prime, so that's the square root. And if you screw this part up, yeah, you're going to screw the rest of it up, but you got to figure this out. You square the whole thing, so it is 25 sine squared. I only said that 9,000 times. And that one's 9. So if you did want to combine these, you can. You don't have to, but you pull 9 of the sine squareds off, and you're left with 16 sine squareds. And the sine squared plus cosine squared gives you 9, because you'll have 9 of them. So either one of those is going to work. T is well, right. So technically T is the length, or it's R prime divided by the length of R prime. Then, but you only care about it at pi over 4. So pi over 4. So if you stuck that into pi over 4, on the top you'd get 5 square root 2 over 2 and 3 square root 2 over 2. And then if you stick the pi over 4 into this equation, well, pi over 4 will get square root 2 over 2, but you square it, you get a half. So a half of 16 is 8, so you just divide by 17. Now, finding n and t are really hard, but you only care about it at one point. So don't go through all that crazy math. If you plotted this, I mean, at this point you have to figure this out. That these are all just ellipses or circles or hyperbolas or something like that. So this is this one. It's an ellipse, part of an ellipse. At pi over 4, you're approximately here. So you should at least know that the tangent is a tangent vector, points tangent to the curve. And therefore, the normal is going to point perpendicular to that. Does it point in or out? And the answer is, well, it's in the direction of the curve. So it's like a force. It causes it to push in. So that means that the normal vector is just going to be, well, it's going to have negative reciprocal slope. So, you know, it's your t, except the way you do this is you switch the components. The square root of 17 is just a constant. And you figure out what the signs are going to be in order to make that work. And in this case, they're both negative. So that's all you have to do on that part. For AT, you look in the book or in the thing, and there's a bunch of formulas. One of them is, this is the length of R prime. It's the derivative of the length. So d dt. So you look at that, that's going to be the square root of 16 sine squared t plus 9. Take the derivative of that. So that's going to be 1/2 16 sine squared t plus 9 to the negative 1/2. And then you multiply that by the derivative of what's inside. And that will be, well, the 2 will come down, it'll be 32 sine t and then cosine t. And again, you only really care about this at t equals pi over 4. So you just plug that in and you'll get, let's see, 1/2. You'll get this 17 to the negative 1/2 means 1 over the square root of 17. And then you plug in 1/2 pi over 4, you'll get square root 2 over 2 times square root 2 over 2 times 32, and that's equal to 16. So it will be 8 over the square root of 17 to get a sub t. To get a sub n, the formula in the book says it's the length of the acceleration vector squared minus the answer you just got squared. So you find the length of the acceleration, that's going to be, again, 25 cosine squared t plus 9 sine squared t plus minus the answer that you just got squared. So that goes in there as 64 over 17. Now when you plug in pi over 4, you'll get square root of 17 minus 64 over 17. So there's your answer. If you don't like that, you can clean it up a little bit and you'll get 15 over the square root of 17. For curvature, there's a couple different formulas, but one of them is that x prime, y double prime, and y double prime x prime thing. So you'll get minus 5 sine t times minus 3 sine t minus 5 cosine t times 3 cosine t all over, and then it's the thing we just already had, so 25 sine squared t plus 9. Sorry, that's that one of those is cosine t, and 9 sine squared t, and then to the 3/2 power. So then you put that in. Well, first of all, the top is just 15 sine squared plus 15 cosine squared. So the top is 15. In the bottom, we get lots of these 17s and then raised to the 3/2 power. So whatever that term, that's the answer there. For the next one, if you don't know how to take derivatives at this point, yeah, the problems are going to be really hard. So not sure what to say about that other than Calc 1. X squared y plus xy cubed, you probably should put it to the -1 power or do quotient rule a bunch of times. So the first derivative will be, you just go -4 times x squared y plus y xy cubed to the -2 multiplied by the derivative of the inside with respect to x. So 2xy plus y cubed. And then fy, same thing, -4 x squared y plus xy cubed to the -2 multiplied by the derivative of the inside, which is x squared plus 3xy squared. And then you just repeat that process for the other two, and you're going to have some product rules and stuff in there. And I think just for I'll do one of them. Fxx, take the derivative of this. You're going to have a product rule, and you're probably going to have a chain rule. So let me just group them. Or just multiply the n by -4. It doesn't matter. So you do the first, so -4 x squared y plus xy to the cube to the -2 times the derivative of the second one. So that's just going to be 2y plus the second one, 2xy plus y cubed times the derivative of the first. So the derivative of the first is going to be 8 x squared y plus xy cubed to the -3. Then you multiply by the derivative of the inside, it's going to be 2xy plus y cubed. So you end up getting these repeat kind of things. Don't have to simplify it out. That's just, that'll take forever. So there's fxx. You can do yy and xy very similarly by the derivative there. And then the last one, once again, if you can't take derivatives, then that's going to be hard. The gradient function is you do each of the separate derivatives. So you can rewrite that as x squared plus y squared plus 1 to the -1. So when you take the derivative, you've got -1, this thing to the -2 power, which means it's going to be on the bottom squared. And then the top will be minus, and then you take the derivative of the inside will be 2x. Similarly, you'll get -2y over x squared plus y squared plus 1 squared. So that's the gradient. At the point 1, 1, you just plug in 1, 1. This thing will be -2/9 -2/9. That was part A. Part B, find the level curve at that point. Well, if x is 1 and y is 1, then you plug that into your function and you'll get z equals 1/3. So you want the level curve 1/3, where z is 1/3. So that means that the level curve will be 1/3 equals 1 over x squared plus y squared plus 1. You can flip both sides and you'll get 3 equals x squared plus y squared plus 1, or 2 equals x squared plus y squared, which is the circle of radius square root 2. And then you just go to the point 1, 1 and draw your vector. And as we said in class, these things always point perpendicular to the curve. It's the whole point of these things. And so that's the picture there. I don't think I have enough room. The other one said find the directional derivative in the direction. So you take the gradient and you dot it, not with the vector, but with the unit version of that vector. So that was the only little sneaky part there. So you have -2/9 -2/9 dotted with, well, the direction in the vector. The original vector was 2, 0, but you need a unit vector. So you just turn it into, it's 2i versus i. So you end up getting -2/9. If you did a dot product and got a vector, then that probably gave you 0 because you don't know what you're talking about. The maximum derivative is always, and this is in the theory, is you just take the length of the gradient vector. So that's the square root of 4/9 plus 4/9, which is the square root of 8 over 3, or if you prefer 2 square root 2, sorry, not 4/9, 4/81, 4/81. So it'll be, that's a 9. So 2 square root 2 over 9. So and again, it's not a vector, it's a derivative. So it's a number. And then the extra credit you just needed to know any place where this was 0. So that means you just take your gradient, which was, you dot it with something in order to get 0. So minus 2/9, dotted with something to give 0. And technically, you're not supposed to use 0 vector because it's not a unit vector. So you just need a unit vector that goes in here. I can't remember if it was a unit vector or not. Maybe not. Maybe we'll just find any vector. So, that doesn't make sense. So that's all right. I didn't take off to do that. So anything that causes this to be 0, which means something like minus 1 and 1, they have to be opposite signs and they have to be the same value. So divided by 2. So that's probably it. Or -1 divided by 2. So I think one person got that. Okay. All right. So that was test 3. I could get bogged down in the algebra for sure. It was not. I mean, the tests are. This one was long because there was a lot more material. But it's not really, the tests are not really meant to be learning experiences. If you're getting to the test and you have to figure out what the topic is, then yeah, it's going to be hard. They're supposed to be more reactionary. Can you do these things? One we did in class. So anyway, enough of the gloom and doom. If it wasn't as good, well, let's just see what happens on the test 4 and on the final. And if you recover nicely, then this won't cream your grade. If it is more of a symptom of, I'm not doing any of the homework and I'm not asking questions in class and I'm not really trying, that's something that needs to be fixed. So please do that. Now, if you look at the schedule, basically, today is 13.3 and 13.4. That's today, and so that's Thursday. Friday is 13.5. Monday is 13.6, and then pretty close. I think then we have one more test on that final stuff. Yeah, Tuesday, and again, probably just kind of thing. We'll do as much as we can in the morning, and then. Well, no, actually, I think we want to do. I should say this. So Monday is this. Tuesday morning is going to be test 4. Tuesday afternoon is going to be review, and then Wednesday morning is the final. So I'll try to give you like kind of a practice final or some kind of outline that shows what kinds of questions might be on there. So that'll come out pretty soon. All right, so with that in mind, let's see, 13.3 is really just a follow-on for 13.2, but it's just another way of doing these volume calculations. So it's double integrals in polar coordinates. So it may look ugly to begin with, and your polar skills are, plotting these things can be tough, so practice up on that as well. Again, the idea is that the volume is going to always be the double integral over the region of your function dA is the way we write it. So volume is given by this mess of symbols here. Now you can, in order to compute it, you have to draw the region and then figure out, is it bounded like top and bottom or left and right? You determine whether you really want to write this as the integral of f of x, y, dy, dx. And if you do that, then you'll have a function of y and a function of y for the bounds. And then you'll have like numbers x1 and x2. So again, curves on the inside, numbers on the outside. And it's an iterated integral, but I'm dropping the parentheses because it looks like that for a while. Or if you want, you can write this as fxy dx dy. And now you've got x, like x1 as a function of y and x2 as a function of y. And then you've got y1 and y2. But again, numbers, curves. And Sometimes the book says do it both ways, and maybe see which one is actually then easy to integrate. But that's all Calc 2 stuff. Calc 3 is in the setup. Calc 2 is in the execution. And this came again from taking your region R, chopping it up into pieces this way, chopping it up into pieces this way. You had lots of dx's or delta x's, which became dx. So you've got lots of delta y's, which became dy, and that's the way this works in rectangular coordinates. So how does this work in polar? Is that instead of chopping it, where you're chopping your x and your y, you're going to be chopping up your theta and your r. So the region will look kind of like, again, here we have some region. I'm going to chop it up in thetas. So that means thetas, they're angles that come out from the origin. And then I'm going to chop it into radial lengths out. So it's kind of like a web or radar signal or something, holograph paper, if you've ever seen that before. So then we got to come into these little things in here and figure out. It's not like dx times dy anymore to get that little area. So what we want to know is we basically want to know the area of this sector here so that we can get our Riemann type sum, and then we can take a limit. And this is where there is a little bit of a twist to it. I think maybe we could go through the derivation, but I think maybe we won't for now. We can come back to it if knows why this works. It's not, so again, yeah, we come back over here, we want to figure out our little area here, like the little d, don't write d, our little delta A of any of these little things is just length times width. So that's delta x times delta y. And that's why this becomes over here is dx dy or dy dx. The little delta A becomes dA, and it's just length times width. But now the problem is my dA is no longer as easy as that. It depends on the angle. This is true. It will depend on the delta of the angle. It also will depend on how much the R changes. I think that probably makes sense. So you kind of want this. But it actually depends on how far out you are. So you can't just go delta R, delta theta, because down real small, delta R and delta theta will give a small block. But if you go further out, these get wider and wider and wider and wider. And so you can't just say, well, I'm going to look at how far apart the R's are and how far apart the thetas are, because the theta ends up being wider and wider and wider, and these things range out. So the difference is this. You actually is how far out you have to go as well. So this is like the new twist on is that the dA includes this extra little piece in it, so that, and really I should write, speed up here, delta A turns out to be this, so then when we take the limit, we get that dA is R, dR, and d theta. And that's the new thing. So when we convert the dA, we get this. But we also have to remember we have to convert covert. We need to convert our f of xy by converting. All the x's are going to become r cosine theta, and all of the y's are going to become r sine theta. It's like, that's the regular polar transformation. All the x's and y's have to convert to what they are in polar. So how does this work in practice? So for example here, this is actually 13.3.1, so you can see the picture in the book. It says find the volume, and again it says, these are all signed volumes, they could be negative. So find the signed volume under the plane z equals 4 minus x minus 2y, above the disk bounded by x squared plus y squared equals 1. So a very brief sketch of what this looks like is you have a plane. It's coming in like this. You've got your circle down here in the XY plane. And then you lift that circle up until you hit the plane. Well, it's going to kind of look slanted here. And so you just keep drawing lines until it looks right. So you've got this kind of like cylinder that's, the top is not flat, it's been sheared off at the top. So it looks exactly like that. So it's a cylinder with a, that's kind of had the top chopped off of it. But anyway, the formula, regardless of which technique you use, is that the volume is equal to the double integral over the region of your 4 minus x minus 2y dA. That is by definition going to be your formula for the volume. But computing it is a little tricky if you think rectangular, because what is the region R down here in the bottom? If I draw R by itself, it is a circle. That's the, again, think of this as the shadow region under the object. So in order to do this, you'd have to figure out what the bounds are, dx or dy. If we do one of them, let's just say, let's try to figure this out, where we do curves for y and we do numbers for x. Well, the numbers for x are not, will end up not being too hard, it'll be just minus 1 and 1. But the curves, it's like the top half circle and the bottom half circle. So if you come over here and solve for y, you get plus or minus the square root of 1 minus x squared. So that means the lower curve, which is the lower half circle, will be negative the square root up to the positive square root, like that. So if you then try to put this into this integral here, so there's your characterization of r, you would get the integral from negative 1 to 1 dx, and then you would get the integral from negative the square root of 1 minus x squared up to 1 minus x squared of 4 minus x minus 2y, and then you integrate that dy. It's not the worst one in the world, but it is annoying. You'll have some u substitutions in there, probably, and I guess you can do it. For completion's sake, it's also the integral from negative 1 to 1 of negative 1 minus y squared up to 1 minus y squared of 4 minus x minus 2y, and then dx and then dy. So if you reversed it and you thought left and right with curves and numbers are up and down, that's the other rectangular one. So you could do it, but I think it's good to practice the polar stuff. So in polar, I think we can do it on the other side. How do you characterize this disk? So basically, R is going to be between two functions. This is like my curves, and theta is going to be between two numbers, two angles. So that's like my number. I'm never going to do, well, yeah, I'm pretty sure I'm never going to do like R d theta dr. So again, my dA is always going to be in this order. R, and then I do curves for R, and then I do d theta as angles. So you have to figure out how to characterize this using polar curves. Well, maybe it's not too hard to see that the angle is going all the way around. So at least we know that the theta is between 0 and 2 pi. It's wrapping all the way around. The R, in this case, well, the outer curve of this thing is x squared plus y squared equals 1. So if you convert that to polar, so there's going to be two parts to this problem: converting the curves to polar, and then putting in what the bounds are. So this one we did when this was, I think, one of the very first ones we did in the polar section. That's just the curve r equals 1. So that's super nice. X squared plus y squared is r squared. X squared root is just r equals 1. So the outer curve is always 1. It's sort of moving now, not left to right or top to bottom, you're moving from the origin out. What's the inner curve on this? Well, it turns out, I mean, you're going to get every single point between 0 and 1. So this one will make more sense when we start getting holes in it, but that 0 means like the inner curve, and there isn't one yet because there's no hole in it, to the outer one, which is the circle, which just has this equation, r equals 1. So now if you go back to, this is my characterization of r. So that means that the volume, which was the double integral over the region of 4 minus x minus 2y dA, can now be written in polar as r dr d theta. That's what dA becomes. The r curves go from 0 to 1. They look like numbers, but they're actually curves. The theta is 0 to 2 pi. And now I got to convert the inside as well. This will be 4 minus r cosine theta minus 2r sine theta. So the x becomes r cosine, the y becomes r sine. So if we wanted, so that's the setup. That's this curves. This is numbers on the outside. We probably should distribute the r through. We'll get the integral from 0 to 2 pi, 0 to 1 of, I don't know if I can squeeze it in here, but 4r, just distribute the r out, minus r cosine theta minus, r squared minus 2r squared sine theta, and then dr d theta. So now it just becomes like a regular integral. You do the r's first, thinking of theta as constant, plug in the bounds for r, then do theta next, and then you'll have your answer for the volume of that truncated, sort of cropped off cylinder. So just for completion's sake, if we integrate this, 4r will become 2r squared. This will become 1/3 r cubed cosine. The other one will be 2/3 r cubed sine. And then we plug in the bounds from 0 to 1 for r. And again, those are r numbers. So getting a little bit funky here, but we get the integral from 0 to 2 pi. We plug in 1, you'll get 2 minus 1/3 cosine minus minus 2/3 r cubed sine. When I plug in 0, I get nothing. So I don't get anything there. Boom. All right, now if I integrate with respect to theta, I'll get 2 minus 1/3 sine plus, oh, no, that's gone. I plugged in 1. 2/3 cosine, and then I plug in 0 to 2 pi. And I'm running out a little bit of room here, but if you plug in 2 pi, you'll get, this 2 will be here, or 2 theta, so that's 2 theta, right? I'll plug in, I'll get 0 for sine, I'll get negative 2/3 here, then I plug in 0, and I work it all out, 0, 0, 2/3, and in the end, you just get 4 pi. Sorry, I don't have a room there, but whatever that is. Whatever the units are cubed, so that's 2 theta. So the hard part is in the setup, trying to figure out what the curves are, converting them to polar in order to get the bounds, remembering that the dA is r dr d theta, and work from there. All right, let's do a quick little break here. Come back in like 5 minutes, and then we're going to do some more of those, and then see if you have homework questions or anything else you want to talk about. So back at like 8:12. So see you then.